Hello everyone, I am Suhas Tumkur Chandrasekhara and today I will be giving a presentation on implementation of pattern recognition techniques for email spam filtering. This project and presentation are done as part of the course EEL6825 pattern recognition for the term Spring 2017. So this will be the outline of the presentation. Firstly, I will provide a brief introduction on spamming and email spamming. Next comes the motivation for this project. It will be followed by the methods used in this project for email spam filtering. I will then present the results of running these algorithms and provide a conclusion. The final part of this presentation will be the project demo where I will be running these algorithms and displaying the results. Coming to the introduction, I will address what is spamming. It is nothing but sending the same message indiscriminately to a large number of recipients. It is an attempt to force the message on people who would not otherwise choose to receive it. Often these messages are unsolicited and of commercial value. Most common form of spamming is email spam. Now let's see what's the need for filtering out such spam emails. Spam emails get past all security and gets into the inbox of recipients. They may contain malicious content or make the recipient install some malware on their systems or deceive the users to sharing their personal credentials like say such as bank details or passwords or anything like that. Also, I myself have experienced that because of the amount of spam emails that are present in the inbox, it gets cluttered and I lose track of an important mail between these spam emails. So that's a big problem and that needs to be addressed. It's also notable that on an average 400 billion spams are sent out in a day and spammers use fake email IDs to send out such emails. Thus, we definitely need a filter that would separate out spam emails from the regular or ham emails and doesn't let them enter into our inboxes. Now let's understand how classification works as we need to use this methodology to classify emails as spam or ham. It is a technique of assigning a newly observed data to one of the predefined set of categories. In our case, newly observed data would be an incoming email, maybe a spam or ham, and the set of categories, predefined categories would be spam and ham. The classifier model is built by training it with past data to identify if a mail is spam or ham based on the various attributes like sender or maybe the subject line of the email or frequency of certain characters or words and so on. So moving on, these are the three algorithms: naive Bayes, support vector machines SVM, and k nearest neighbors KNN that I will be using in this project. First, let's see what naive Bayes is. Naive Bayes is a classification algorithm. It employs the method of probability to classify the data. Now let's see this figure. So as per this figure, prior probability of a data record to be blue is nothing but number of that records that are blue divided by the total number of records. So I have counted the number of blue records in this picture and that's 38 and the total records is 59. So that amounts to 0.64. And similarly, the prior probability of data record being purple is 0.36. The next type of probability is the likelihood probability. And as seen in the figure, the new point A needs to be classified. So the likelihood of the point A being blue is given by the formula number of blue records near A divided by the total number of blue records. So that amounts to 2 by 38, which is 0.05. Similarly, likelihood of A being purple amounts to 0.14. Next is the posterior probability. So posterior probability of the point A, which is to be classified being blue, is nothing but prior probability of blue, which we saw in the previous slide, times likelihood of A given blue. So that is 0.0320. Similarly, posterior probability of A being purple amounts to 0.0504. So generalized formula of naive Bayes is as shown, where C is class and X is attribute, and probability C by X is posterior probability of the class given some attributes, and P of C is probability of class, prior probability of class. P of X given C is likelihood of an attribute given a class, and P of X is nothing but prior probability of an attribute. I have used the Gaussian model in implementation of naive Bayes, and this is the probability distribution of new data V given class C. And in our case, the probability that a mail is spam given some attributes is probability of likelihood of the attribute given spam times probability, prior probability that the mail is spam, and the entire thing divided by prior probability of the attributes. And as I was saying, I have used the Gaussian model in the implementation of naive Bayes. The results of this are documented as shown. The accuracy is about 81.3%, and the time taken to run this algorithm was 0.47 seconds. The second algorithm is support vector machines (SVM) that I have implemented. It classifies various cases by creating a hyperplane in an n-dimensional space where n is nothing but the number of attributes. Support vectors are nothing but coordinates of each data record in the data set. So you can see that in the diagram here, all these points are nothing but support vectors. The entire working of SVM actually depends on identifying the right hyperplane which is able to divide these points into separate and distinguished classes. So let's see how that's done in different in all of these cases. So in the first one, that is two distinct classes, there is a clear distinction between the blue stars and the red circles here. And so the easy way to obtain the hyperplane is hyperplane B, which very clearly distinguishes both these classes. And when you see the margin rule, it's also possible that we can have three hyperplanes which all three of them divide these two into separate classes. But in such a case, what SVM does is it picks the hyperplane which maximizes the margin. So what is a margin? Margin is nothing but the distance between the hyperplane chosen and the nearest data point to it. So in case of margin rule here on the figure, C becomes the optimal hyperplane. And the case of distinct class versus margin, uh, in this option on the figure, we can see that there are two hyperplanes, A and B. A divides both of them distinctly, very distinctly, but its margin is less. But however, if we see the hyperplane B, um, it does not distinguish the blue stars and the red circles very clearly. There is a presence of one blue star on the right side, but it has a higher margin. So in this case, SVM picks up the hyperplane which clearly distinguishes the two classes and not the one which has more margin. Coming to the state of outliers, SVM in such a case would consider this hyperplane and ignore the one blue star that is present on the wrong side of the hyperplane. So moving on. Uh, this is one more of those cases where you can see in this diagram that there is no possible linear hyperplane that could distinguish the red circles and the blue stars here. So what SVM does in this case is it adds a new dimension, a higher dimension, z, and that is calculated by x square plus y square, and then it plots these data points on z and x axis. And once that is done, as you can see, now we are able to have a linear hyperplane, and this sort of mechanism is called kernel trick. So I have used three kernels for SVM: linear, polynomial, and RBF. This figure shows how each of these classify data points. The results of this running all these three are shown in this table. We don't see much of a difference in performance of these kernels, but this can be attributed to the fact that input data set that we are using in this project was already very clearly separated, and it didn't actually need the addition of a new or higher dimension to it. So all of these kernels perform in a similar sort of way. The performance is comparable, very much comparable. Moving on, the last algorithm that I've implemented is the k nearest neighbor (KNN) algorithm. This employs a technique called as nearness. Let's understand its working through these figures. So as you can see in the first figure here, the goal is to classify the black star as a blue circle or green rectangle. So KNN employs voting technique from the nearest data points. The number of data points it will consider is denoted using the K. That is what K stands for in KNN. So let us assume or consider that K is equal to 3 in this case. Then it will consider the nearest 3 data points measured by a distance function. I'll talk about the distance function in the next slide. Let us say it took the 3 data points as shown in the next figure. So in that case, the choice from all the 3 neighbors is blue, and hence the black star will also be classified as a blue circle. As we have seen, the answer can vary depending on the value that we set for K. So how do we choose this K? So the rules for that are K cannot be too small as it will overlook noisy data, and the other condition to be considered is that K cannot be too big as well as it will lead to over smooth boundaries. So as I said, this is the distance function that I have used. Euclidean distance is what I've considered. So that's the formula for calculating the distance function. And this is the plot of the results for the varying values of k. So I have run the algorithm for k equal to 5, k equal to 10, k equal to 15, 20 and 40, and these are the corresponding results. So we can very clearly observe a pattern here. So when k was 5, the, the accuracy was 80%, and as k increases, the accuracy you can see keeps on decreasing. Also, if you observe the run times, starting from k and moving till up to 40, the runtime increases. So the pattern suggests that k value, as and when k value is increased, the accuracy goes down and the runtime taken to execute the algorithm increases. So let's now see which is the data set used for this project and some details about it. So data set that I've used in this project was downloaded from University of California, Irvine UCI database. It's a multivariate database with 4061 instances, out of which 1813, which amounts to 39.4% of the entire data set, are spam. And it also has 57 attributes attached to it. And the last column of the data set contains either a 1 or a 0, uh, which is to indicate whether the given email is either a spam or ham. 1 stands for spam email and 0 stands for ham email. It also provides some insight into number of letters in uppercase and the character or word frequency, which will be helpful to classify the email as spam or ham. So that's the dataset description. So finally, let's see the summarized results and draw conclusion. So these are the all the three algorithms results are tabulated in this table. So you can see very clearly that KNN, for any value of KNN actually is not that, doesn't have that great a performance. Both its runtime is more and its accuracy is not corresponding to that runtime. So amongst the three algorithms that have been considered, it is safe to say that KNN is the least performing one in terms of both accuracy and runtime. From this table of results, it is evident that KNN has lesser accuracy and also takes a lot more time than the other two. This table also is indicative of the fact that SVM is the best of the lot, as its accuracy as compared to naive Bayes is significantly more, while the increase in the running time of SVM is only fractionally more when compared to that of naive Bayes. Another key takeaway from this is that among the three kernels of SVM, we do not actually see much fluctuation in accuracy or runtime for that matter. This can be tied to the fact that the input dataset considered in this project, which is the spam-based dataset from UCI, it is already well separated and it has a clear distinction between classes. So there is no such need to introduce a new or higher dimension. So that is the reason that all three kernels' performance are very much comparable and similar. These are the references that I've used for this project, and that's the end of the slide presentation. Next, we'll see the project demo. So this is the code for naive base. Here we see that the split ratio I have divided as 75-25, where 75 is for the training data set and 25 is for the testing data set or the validation data set. And you can see here that this is the spam based data that I have downloaded from UCI website. So now let's go ahead and run naive base. So yeah, this is the output that we get. The split of the entire data set of 4601 instances was 75-25, 3450 instances in the training data set and 1151 instances in the testing data set. And you can also see that the accuracy is 83.4% and time taken was about 0.52 seconds. Next, we'll move on to the SVM algorithm. In the SVM algorithm, we can see here that again the split that I have used is 75-25 for training and testing data sets. Also, I am running all these kernels, linear, polynomial, and RBF kernels at the same time, and I'm calculating the time taken by all these three combinedly or cumulatively and printing it on the console. So let's run SVM. So that's the output. Yeah, the training and testing is in the ratio 75-25, and the individual accuracies of all these kernels has printed 93.2, 93.8, and 93.7. As I said, they're very much compared and not much difference in their performance. And the cumulative time for all these three kernels was 2.8 seconds, around 2.8 seconds. Now let's go ahead and execute the final algorithm that I've implemented, that is KNN. Here also I have made use of 75-25 ratio for the training and testing data sets. And for this particular run of the algorithm, I have considered the case of k equal to 5. The nearest neighbors considered is equal to 5. So during the presentation, I have said that I will run this for 5, 10, 15, and so on. So I have run this algorithm individually for all those k values and plotted those results. So right now the run is happening for k is equal to 5. As I said, it's going to take some time. So let's see the code of KNN during that time. Yeah, this is the split ratio 75-25, and this is the number of neighbors to be considered, which I have set for k equal to 5 for this particular execution. And you can see that herein I am dividing the entire data set into two sets, which is training data set and the test data set. These are the 57 attributes that are actually present in the data set that I have downloaded. So let's see if we have gotten our output for this case. Not yet. That's because it takes around 1.5 minutes to execute, around 80 to 90 seconds. That's why we have classified that as the least performing algorithm out of the three considered: naive Bayes, SVM, and KNN. And because of all these emails filtering techniques, spammers have now come up with putting in images and putting in text in those images instead of writing it on the email, so that it is an image and text classification cannot happen. So to avoid or filter such spam emails, we will have to go for image recognition techniques and build our email spam filter based on that. So that's the output. As you can see, the accuracy is around 79%, which is still very less when compared to SVM results, which is 93%. And the time taken was about 153 seconds. You can, it's not even comparable. All these three combinedly together took 2.8 seconds, and this alone is taking 153 seconds. So that's about 2.5 minutes for its execution, and that's why it's the least performing one out of the three chosen. So this concludes the demo as well as the project presentation. Thank you very much.